Hello and welcome to this ICALP presentation. My name is Daniel Neuen, and in the following I will speak about hypergraph isomorphism for groups with restricted composition factors. Okay, so as the title already suggests, this talk is about isomorphism testing. So let's start with defining the main problem, which is the graph isomorphism problem, where the input consists of two graphs, G1 and G2, and we want to find out whether they are isomorphic. So whether there is a bijection from the vertex set of the first graph to the vertex set of the second graph, which preserves the edge relation. And, well, in this talk we want to look at algorithmic aspects of this problem. So in particular, the following two algorithms are the starting point for our work. So the first algorithm is Lux's polynomial time isomorphism tests for graphs of maximum degree d. So it solves the graph isomorphism problem for this class in time n to the O of d. And well, for the graph isomorphism problem, or for research on graph isomorphism, this algorithm had actually a huge impact because it was the first algorithm that introduced techniques from group theory in a really advanced manner to the algorithmic framework tackling the graph isomorphism problem. And, well, the methods of Lux then in the following decades have not only been used to solve this graph isomorphism problem for graphs of maximum degree, but they actually have been used for a number of isomorphism tests tackling a number of different restricted classes of graphs. And even more importantly, and beyond that, the methods of Lux's algorithm form also the starting point for Babai's quasi-polynomial time algorithm. So the famous breakthrough obtained by László Babai in 2015 showing that the graph isomorphism problem can be solved in quasi-polynomial time and to the polylog n. And, well, the basic approach of Babai's algorithm is to follow the recursion techniques introduced by Lux's algorithm and then simply attack the obstacle cases where the recursion by Lux's algorithm doesn't lead to the desired running time. And in this case, Babai develops various new techniques also on the group theoretic level to basically tame these cases where Lux techniques don't suffice to obtain the quasi-polynomial time bound. Okay, of course this now raises the natural question whether we can also use the techniques introduced by Babai to obtain further progress for restricted classes of graphs. And in this direction we could obtain a first positive result about 2 years ago. So in a joint work with Martin Grohe and Pascal Schweitzer, we could show that the graph isomorphism problem for graphs of maximum degree can be solved in time n to the polylog d, thereby generalizing both Babai's algorithm, improving the dependence in the exponent from number of vertices to maximum degree of the input graphs, and also generalizing or strengthening Lux's algorithm, improving the dependence in the exponent from linear in D to polylogarithmic in D. And the basic approach is essentially to extend the techniques introduced by Babai's algorithm to the bounded degree setting, and also introduce some new normalization techniques. It's also a part of the algorithm. Okay, now of course, given this result from 2018 with the improved complexity for graphs of maximum degree, there are a couple of natural follow-up questions. And, well, the questions that we will look in this talk are the following. So the first one is essentially, well, we have obtained a better complexity for graphs of maximum degree, but naturally we can also ask for other graph parameters. So the question is, for which graph parameters can we solve the graph isomorphism problem in time n to the polylog of the parameter in question? And somewhat closely related to this first question, there is the second question, which is about, well, remember that I said that Lux's algorithm is used as a subroutine in a number of different isomorphism tests, for various other graph classes. So naturally what can wonder is, now that we have improved the complexity of Lux's algorithm from m to the O of d to n to the polylog of d, can we also obtain improvements for all of these isomorphism tests that use Lux's algorithm as a subroutine? And these are the two questions that we want to explore in the remainder of this talk. Okay. Now to do so, the first thing that we have to do is we have to understand how all of these three algorithms actually tackle the isomorphism problem. And the common feature here is a problem that is called the string isomorphism problem. So let me introduce the problem. The input to the problem are, well, first of all, two strings, x and y, which are defined over some finite ground set omega, and which map into a finite alphabet sigma. And additionally, we are given a permutation group, so a subgroup of the symmetric group over the ground set omega. And, well, here it's important that this group is only represented implicitly by a generating set. Yeah, so think of omega as being exponentially large in the size of the ground set omega, but the representation of gamma is only of polynomial size. Okay, now the question is whether there is some permutation in this group gamma that proves x and y to be isomorphic. So applying gamma to x turns it into y. Yeah, where applying a permutation gamma to a string x is basically just done by permuting the elements of the ground set accordingly. So for example, if we have a permutation gamma that maps 1 to 2, 2 to 3, and 3 back to 1, and we apply it to this string x here over alphabet AB, then for example, this A here in the first position is just mapped to the second position. Yeah, the A in the second position is mapped to the third position, and the B in the third position is mapped to the B in the first position, and just according to gamma. Okay, so this is the problem that is considered by all of these three algorithms that we have seen on the previous slide. So let me just state the connection to graph isomorphism. Well, this problem is more general than graph isomorphism, because what we can simply do is, given two input graphs, G1 and G2, we can look at the corresponding adjacency matrices and just interpret them as strings. For example, by just concatenating the rows of the matrix. And then the two graphs are isomorphic if and only if we can simultaneously permute rows and columns of the first matrix in order to transform it into the second matrix. And well, this set of operations, simultaneously permuting rows and columns, this gives rise to a group gamma, a permutation group over the positions, which then forms the corresponding input group, which can also be compactly represented. Actually, there is a generating set of size 2. Okay, so now this is how all of the three algorithms actually tackled the graph isomorphism problem. Now, of course, well, when we look at Babai's algorithm, it's kind of natural how this works, because we can just apply this reduction here to get the corresponding instance of the string isomorphism problem. On the other hand, when we look at Lux's algorithm, the situation is far less clear, because, well, we have the restriction on the input graph, but it's not clear how we can translate this to a restriction of the corresponding string isomorphism problem. In particular, the way how all of these algorithms use the string isomorphism problem is that they actually try to work with the group gamma here. So instead of decomposing or working with the graphs or the input structure, we actually work with the input group, which allows us to use all kinds of results from group theory. So coming back to the bounded degree setting, what we would ideally like to have is, we would like to have a reduction that, well, allows us to translate restrictions on the input graph, like bounded degree, to restrictions on the input group. And, well, here it turns out, this was already observed by Lux in his work, that the right notion here is the class of gamma D groups, which are all groups, gamma, for which every composition factor of gamma is isomorphic to a subgroup of SD. Okay. Now, if you don't understand this definition, don't worry, it's not going to be important for this talk. In this case, just think of groups gamma that are somehow composed of subgroups of SD in a well-defined way. Okay, and now the important theorem that connects the graph isomorphism and the string isomorphism problem for restricted settings is that the graph isomorphism for graphs of maximum degree D polynomial time Turing reduces to the string isomorphism problem for the gamma D group. So what we actually want to do is we want to solve the string isomorphism problem for this class of groups. And this is exactly what Lux's algorithm achieves. It solves this problem, the string isomorphism problem, in time n to the O of D, given the input group is a gamma D group. Okay, and well, it actually turns out that the same approach is taken by our algorithm from 2 years ago. That is, what we actually prove is that the string isomorphism problem for gamma D groups can be solved in time n to the polylog D. thus improving Lux's algorithm also for the string isomorphism problem. Okay, and then using the reduction from the previous slide, we get the desired result on the graph isomorphism problem for graphs of maximum degree D. Okay, so now this is the state of the art from 2 years ago. So what are we doing in this work now? Well, remember that one of the questions I raised at the beginning of this work is that, well, Lux's algorithm is used in a number of different algorithms tackling the isomorphism problem, and given the improvement that we obtained, it seems natural to hope that we can now speed up all of these algorithms that use Lux's algorithm as a subroutine. Yeah, basically replacing the subroutine for the string isomorphism by our new algorithm. Okay, so to now explore this question, let's start by having a look where Lux's algorithm is actually used as a subroutine. And it turns out there are actually quite a number of isomorphism tests. So here I have listed a couple of examples. I don't want to really go into the list in detail, but let me just point out a few results. So for example, Lux's algorithm has been used already early on to obtain a polynomial time isomorphism test for graphs of bounded genus, which was then actually generalized in the early 90s by Ponomarenko to an isomorphism test which solves the graph isomorphism problem for all graph classes that exclude a fixed graph as a minor, which was then even further generalized actually to topological minors by Grohe and Marx. And well, also in the last years there have been further examples of applications of Lux's algorithm to certain classes of graphs. Okay. So now coming back to the original question, whether we can now get improvements for all of these algorithms by improving on the string isomorphism subroutine, well, the immediate answer to this question, unfortunately, is no. So let's explore why this is the case. Well, the reason for that is that most of these algorithms that exploit Lux's algorithm as a subroutine do not so by solving the string isomorphism, but some closely related problem for which Lux's algorithm also works. So in particular, when we look at the input to the string isomorphism problem, there are kind of two types of variations that can occur. The first type occurs in the input group, where, well, these algorithms, where we do not always consider the class of gamma D groups, but also consider slight variations, where, for example, we can allow abelian groups as composition factors, or also where we can allow to combine groups that are sort of almost gamma D in certain well-defined ways, which then leads to this notion of gamma D towers. Okay, so that's the first variation. And then there's the second variation, which is on the input structures, where we may not only consider strings, but also more complicated objects, like, for example, hypergraphs, or any type of hereditarily finite object that is built by iteratively nesting sets and tuples. Okay, and it works out that Lux's algorithm, maybe with a few modifications, actually works for all of these settings. And, well, as you can maybe already think, this is what most of the algorithms from the previous slide exploit. So in particular, when you take a closer look, a very common extension that is used is the hypergraph isomorphism problem. Okay, so now this leads an immediate question, which now also brings us to the title of this paper, namely whether we can, well, lift the result, the n to the polylog D algorithm from 2 years ago, from strings to the setting of hypergraphs, attaining hypergraph isomorphism for groups with restricted composition factors. And the main technical result of this work is that this actually can be done. So the hypergraph isomorphism problem for gamma D groups can be solved in time n plus m to the polylog D, where n denotes the number of vertices of the input hypergraphs and m the number of hyperedges of the input hypergraphs. Okay, so I don't really want to talk about the proof of this theorem or how the algorithm is built. So let me just say that sort of the main ingredient is that one has to find a way to lift the local certificate routine, which is kind of the main group theoretic routine of Babai's algorithm, from strings to hypergraphs. Okay, and let me leave it at that. Okay, so instead what I want to do for the remainder of this talk is I want to look at applications or implications of this improved algorithm for the hypergraph isomorphism problem. And actually the first very immediate implication that we get is the fastest algorithm for the hypergraph isomorphism problem in general. So we have no restriction or no input group given, but we just want to decide whether two given hypergraphs are isomorphic. And well, by the previous theorem, this can be done in time n plus n to the polylog n. Okay, and let me just mention here that actually the same result was proved independently by Daniel Wiepking, and actually this is also presented at this year's ICALP. So if you're interested in that, also have a look at Daniel Wiepking's talk. Okay, so now let's look at some deeper applications of the main theorem here. And well, towards this end, well, the obvious thing to do is let's again look at the list of applications, specifically a list of algorithms that use the hypergraph isomorphism for gamma D groups as a subroutine. And well, specifically what I want to look at here is just one exemplary algorithm, which is Miller's algorithm that solves isomorphism for graphs of bounded genus in polynomial time. Yeah, which in particular uses the hypergraph isomorphism as a subroutine. Now, unfortunately, Miller's algorithm not only uses hypergraphs as input structures, but also uses a second type of variation, namely on the input group. Yeah, remember we had these two types of variations on the inputs. We have the structure of the input, where we switch to hypergraphs, but there is also this variation on the input group, and here Miller's algorithm actually doesn't work with gamma D groups, but with gamma D towers, which are composed of gamma D groups in some well-defined way. And well, it turns out that we can actually get around this notion of gamma D towers. And well, this will be the topic for the rest of the talk now. Okay, so the goal will be to reduce the graph isomorphism problem for graphs of bounded genus to the hypergraph isomorphism problem for gamma D groups. Okay, and to do this, what we will actually do is we will introduce first an auxiliary isomorphism problem. And well, towards this end, we first have to introduce the so-called color refinement algorithm, which is one of the fundamental algorithms in the context of isomorphism testing. Okay, so what does the color refinement algorithm do? Well, the input to the color refinement algorithm is a graph, and the basic idea is that we want to obtain a coloring of the vertices of the graph that essentially represent certain degree sequences of the graph, of the vertices. Okay, so here is how it's done. Initially, we assign all the vertices the same color, yeah, red in this picture. And now two vertices get the same color in some round if they have a different number of neighbors in some color. So initially, where all vertices have the same color, this means that we just color the vertices by their degree. Yeah, so for example, here red means degree 7, blue means degree 4, and green means degree 3. And now we refine this coloring. So for example, we can see that this red vertex here has a green neighbor, but this red vertex here doesn't. So now we can distinguish them and assign different colors to these vertices. Okay, and we can keep on going, iterating this process. So for example, in the next iteration, this green vertex here has a violet neighbor, a purple neighbor, but this green vertex doesn't, so we can again distinguish them. And well, we keep on going like that until no further distinctions are possible, which in this example here now is the case. So if you check this picture, you will see that now the coloring is what's called stable. So for example, both orange vertices have the same color patterns in their neighbor, violet, yellow, and green. Okay, so this is the color refinement algorithm. Now, based on this algorithm, we can now define a class of graphs which are called t-CR-bounded. So a vertex colored graph is t-CR-bounded, where the CR stands for color refinement, if we can turn the input coloring, e.g. into the discrete coloring, that is a coloring where every vertex has its own coloring, by repeatedly performing two operations. One, the color refinement algorithm, and two, we are allowed to split color classes that have size at most t. Okay, so let's again look at an example. So this is the example from the previous slide, and we have already seen what the color refinement algorithm does here. Yeah, this is discoloring that we obtain. Okay, so we have applied the first operation, so now we can apply the second operation, splitting color classes of size at most t, which in this example is set to 3. And you can see here are a number of color classes that have at most this size. So for example, the red color class has size 2. And similarly, the yellow, the purple, the light blue, the green, and the orange color class are small. So now we can all split them, assigning different colors to the two vertices in these color classes, like this. Okay, so now we can see that the coloring is actually not stable with respect to color refinement anymore, so we can split again. And now we can repeat, we have a color class of size 3 again, so we can split. And now you can see that every vertex has a different color, so actually the coloring is discrete, and we have proved that the graph is t-CR-bounded. Okay. And now the main theorem is that there is a polynomial time Turing reduction from the graph isomorphism problem for t-CR-bounded graphs to the hypergraph isomorphism problem for gamma t groups, which in particular gives us an efficient isomorphism test for this class of graphs. Okay, again, I don't want to go into details about proving this theorem. Let me just state that the connection is that what can, well, effectively prove that the automorphism group of t-CR-bounded graphs is a gamma t group. And this is essentially because we are only always splitting color classes of small size, of size at most t. Okay, so now remember that our original goal was to provide a more efficient algorithm for a more efficient isomorphism tests for graphs of bounded genus. So let's come back to this problem, and well, we will use now the isomorphism tests for graphs, for t-CR-bounded graphs that we have seen on the previous slide. Okay, so I won't define graphs of bounded genus here, or the genus of the graph, but let me just state the main property that we are going to exploit, which is that graphs of genus G exclude certain bipartite graphs as minors. Specifically, they don't have a complete bipartite graph on 3 and 4G plus 3 vertices. Yeah, so as well as a well-known example, you can think of planar graphs, which are graphs of genus 0, which exclude K33 as a minor. Okay, and now the algorithm goes as follows. So the first thing that we do is actually we use the standard decomposition into 3 connected graphs and standard dynamic programming techniques to reduce to the case where the input graph is actually 3 connected. Okay, and now by trying out all possibilities, we can fix the image of 3 vertices of the first graph and the second graph by actually assigning a unique color I to vertex vi. And then the main lemma is, well, that this graph that we get there by individualizing 3 vertices turns out to be t-CR-bounded, where t is equal to h minus 1, where the h is this number from the excluded minor. Okay, so then given that lemma, we can employ the graph isomorphism test from a couple of slides ago and eventually obtain our isomorphism test for graphs of bounded genus. Okay, so the main thing is to prove this lemma. So let's see how this goes. So here I've stated the lemma again. And let's assume for a contradiction that this graph is not t-CR-bounded. Okay, so what do we get? We get a set V1 of vertices that have a unique color, and a set V2 where every color class is large, has size at least h. And let's put an edge between 2 color classes whenever there is an edge between 2 vertices from this color class. Okay, and now we can simply perform the following steps, namely, okay, first we can restrict to a connected component of this color class graph. Then we can restrict ourselves to a spanning tree and consider the neighbors in the set V1. And the crucial observation here is that there has to be at least 3 neighbors in the set V1 because the graph is 3 connected. Okay, now we can add these 3 vertices as leaves to the spanning tree and find the unique common ascendant of this vertex, which here is the green class. And now we can simply contract the paths that lead to this descendant here in the middle. And because observe that each of these gray regions is connected, because by stability each of these single vertices must be connected completely to such a color class here. And also each green vertex, again by stability, must be connected to the 3 neighboring color classes. And because this color class is large here, has size at least h, we get the K3H as a minor, which gives us the desired contradiction. Okay, so in total, with what I said on the previous slide, what we get is the desired graph isomorphism tests for graphs of Euler genus at most G. Or actually more general, because remember the only thing that we exploited is that certain minors are excluded, we get a graph isomorphism test for all graph classes that exclude K3H as a minor in this running time here. Okay, so now this brings me almost to the end of the talk, so let me quickly conclude. What we have seen is a faster isomorphism tests for hypergraphs with gamma D groups with this running time here. And then we have seen some applications. So via this notion of t-CR-bounded graphs, in particular, we could obtain an n to the polylog G time isomorphism tests for graphs of genus at most G. Okay. And, well, of course, the natural open question is, can we hope for further applications of this theorem? Yeah, remember there was this long list of many applications where Lux's algorithm is used as a subroutine. And actually what I can report is that by now we could find at least one further application, and that is that we could obtain an n to the polylog h time isomorphism test for any graph class that excludes an arbitrary kh as a minor, which in particular also generalizes the bounded genus isomorphism test. And well, naturally, we hope for further applications in the future. In particular, one open question is whether we can even generalize this result to excluded topological minors. And I think I'll stop here and thank you for your attention.